All right, so welcome to the test 2 review. So we'll go through this section by section. So the first section is this um, chapter 3, part 2, solution. So let's talk about what is a solution, what's a solute, what's a solvent, and what an aqueous solution is. So if we think back to what a solution is, we defined a solution as a homogeneous mixture of two or more things, right? So, for example, Gatorade is a solution, has water, has sugar, has salt. So there's different parts of a solution. You have the solvent and then the solute. The solvent is the major component. So using the example of Gatorade, that would be the water. The solute is the minor component. And so using the same example, the solute would be the sugar or the salt. All right, then we have an aqueous solution. Aqueous is just basically a fancy way of saying water. So water is the solvent. So Gatorade is an aqueous solution. Beer is an aqueous solution. Most of the things you deal with on a daily basis are aqueous solutions because we live in a world filled with water. All right, so to indicate, not only do we want to know what a solution is, we want to know how concentrated a solution is, right? Is this really sugary water or is this not so sugary water? So to do that, we use the term molarity, and molarity gets the symbol big M, and big M is equal to moles of your solute. Again, that's just the moles of the solute over the liters of the solution. That's the entire solution. Cool. Next up, we have dilutions of solution. C1V1 equals C2V2. So C1V1, in this case, they mean concentration 1, volume 1, concentration 2, volume 2. Another way to say that is M1V1 equals M2V2, where these M's are molarities. And so questions like this, you'd have some kind of concentrated solution, and then you dilute it, and then you'd see how much of the initial concentrated solution you need to use, and how much of the dilutant you need to add. So let's say, for example, that you have 6.00 molar of sodium hydroxide, but maybe you want to set up some less concentrated stuff. That way the undergrads don't spill it all over themselves and burn themselves, right? So you want, let's go with 10.0 liters of 1.00 molar sodium hydroxide. So how would you solve this problem? You'd first think of your M1V1 equals M2V2, right? So the question would ask is how much original NaOH solution would you add or would you use? And then you're going to dilute it with water. So maybe another question is how much water do you add? So we have our equation, our M1V1 equals M2V2. So now we just need to identify some things and plug and chug, right? So our original concentration is the 6 molar. So we have that. This V1, we don't know how much we want to use, right? That's going to be our unknown. If we look up next, our M2, what do we want our final concentration to be? Well, we want it to be 1 molar. So we're going to go ahead and plug that into there. And how much of this 1 molar solution do we want? Well, we want 10 liters of it. So we're going to go ahead and plug that into there. We're going to reorganize this algebraically, and you'll get V1 is equal to M2 V2 over M1, right? Divide both sides by M1. And again, we can go ahead and plug these numbers in. So our original concentration was 6 molar. Oops, our final concentration was 1 molar. Our final volume was 10 liters. And then our initial concentration was 6 molar. As you can see, the molar is going to go ahead and cancel out, and then you'll just simply do the math. So let's check it out. 10 divided by 6 is going to be essentially 1.666 repeated liters. And so 3 sig figs. So we'll want to round that to 1.67 liters of your sodium hydroxide solution. So that's how much sodium hydroxide solution you want to add. Next thing you have to think about is how much water you want to add. So at the end, we know our final volume is going to be equal to this 10 liters, right? So final volume is equal to 10 liters. And our final volume is made up out of our sodium hydroxide solution plus our dilutant, in this case, water. And so we know how much sodium hydroxide we're going to use. We're going to use this 1.67. So we can go ahead and plug that into there. 10.0 liter equals 1.67 liters plus the amount of water that you're going to use, and then solve algebraically, and you should get 8.33 liters of water. So at the end, your questions are answered, right? How much water do you add? 10 liters. How much sodium hydroxide do you add? 1.67 liters. So that's how you kind of do those example problems. We had a quiz on it. So most of you should feel pretty comfortable with this type of question. All right, so next thing we learn about is some different types of units. So the first types of units that we learned are percent mass, or mass percent, weight percent. They all mean by the same thing, but it's just basically a weight percentage. So for example, if you have something that is 11% sodium hydroxide by weight, that would be an example of this type of unit. And so you kind of want to think about what your unit is. Is it a conversion factor? What can you do with this unit? What are the 3 parts of a unit? So let's take a look at the 3 parts of the units. First, we have some kind of number. That's a numerical value. Then we have some kind of unit. That could be milliliters, liters, grams, whatever you're talking about. And then you have the actual like subject that you're talking about. What are you talking about? Sodium hydroxide? Are you talking about a solution? You know, whatever. And so the interesting thing to note here is that this is actually a conversion factor. And so it compares 2 things. In this case, it compares the sodium hydroxide to the solution, right? Your solution or mixture is only 11% sodium hydroxide. That means that the other 89% is something else. And so this is a conversion factor you can use to go from sodium hydroxide to solution, or solution to sodium hydroxide. So let's take a look at these numbers. So first thing we want is our number. And we can tell that this part is 11. So you can either write 11 or you can just write 1. And again, this is a conversion factor. So it's something over something else. On the top, we're talking about the sodium hydroxide. On the bottom, we're talking about the solution. So we can put an 11 here. If we put an 11 here, in order to get to 11%, we have to put a 100 on the bottom. So you can do it that way, or you can instantly turn it into a decimal. You can turn it into 0.11, and then on the bottom would be 1. Either way, they both signify 11%. Next up, we're talking about the unit. And we're talking about by mass or by weight. We're talking about a mass unit here, and that unit is going to go ahead and be grams or kilograms. It really doesn't matter which unit you use because they'll all end up being the same thing. But generally in chemistry, you default to grams. So it's grams over grams. So we're talking about grams on both sides of the conversion unit. And then finally, we're talking about our subject. And so this is where things change a little bit. So on the top, what we're talking about our subject is this sodium hydroxide. That one's pretty obvious. It's 11% sodium hydroxide. And then what goes on the bottom, that's what tricks students up quite a bit. And so if it's 11% sodium hydroxide, it's clearly not pure sodium hydroxide. And so on the bottom, you put something like mixture or solution, something like that. So let's see an example of how you would use this conversion unit. So for example, you have 125 grams of 11% sodium hydroxide by weight, how much sodium hydroxide do you have? Right, so we want to think about what we want, and then we want to think about what we have. So what we want at the end is grams of sodium hydroxide. Well, we know we have 125 grams of what? Well, we have 125 grams of 11% sodium hydroxide. So we have 125 grams of mixture. Right? And then the other part that we know we have is this conversion unit right here. So we can plug that right into there. It's another thing that we have. So when we're converting units, generally you want to start with the thing that's not a conversion unit. In this case, it's the 125 grams of mixture. So we put that in there and then we start converting units. So we see where else do we have this type of grams of mixture? Well, we have it down on the bottom right here. So we can go ahead and plug that in. Since this right here is on the top, we're going to want to plug it down in the bottom. So 1 gram mixture, 0.11 grams sodium hydroxide. And then you can see the grams of mixture and the grams of mixture cancels out. And then the only units that you're left with is grams of sodium hydroxide. And then you just go ahead and type this into a calculator. In this case, you end up with, let's go with 14 grams, since there's only 2 sig figs here. So you have 14 grams of sodium hydroxide if you have 125 grams of this mixture. So that's how you use that conversion unit. We'll see a little bit more when we're doing to the stoichiometry, the chapter 4 type of stuff. So another unit that's not used as often, but we did learn, was percent volume. And it's basically the same thing as percent mass, except instead of mass, you're going to use volume. So let's say 11% sodium hydroxide by volume. Again, just as in the previous example, it's a conversion unit. So 0.11 over 1. In this case, now we're talking about volume, right? So we're going to use milliliters. And then again, it's going to be sodium hydroxide over the mixture. So it's just another conversion unit. And then our final conversion units here are ppm and ppb. So let's talk about those for a little bit. Again, these aren't quite used as often. ppm means parts per million, and ppb means parts per billion. So if we wrote out the number 1 million, it looks something like this. And so we could rewrite this as 10 to the 6th. If we wrote out 1 billion, it would look something like this. And we could rewrite this as 10 to the 9th. So parts per million, per. We learned that per essentially means divided by. So if you have something, for example, that's 10 ppm, then you have 10 whatever you're talking about over 10 to the 6th, right, per million. So another unit with this ppm, you'll given by mass or by weight. So let's say by mass or by mole or something like that. So then it's 10 grams over 1 million grams. And then this is your subject area here. So 10 pp by mass, let's say CO2. So this will be CO2, and then this will be mixture, right? But it's just another conversion units. Again, parts per million means however many parts per 1 million. 1 million is 10 to the 6th. And same thing on the other side. Let's say you have 5 ppb of mercury by mole or something like that. And so you could say 5 moles mercury over the total amount. In this case, it's going to be ppb, so it's 10 to the 9th per billion moles of solution. Again, I got this number from right here. I got this billion because it's ppb. I got this mercury from right here. The solution, you do kind of have to assume If you have something that's only part, then there must be other parts of it. So it has to kind of be a solution. And then by mole, I grab that from here. Same thing looking from this other side, right? Where'd I grab this 10 from? I grabbed it right here. Why'd I use mass? Because it says to use mass. Why'd I know CO2? I know CO2 from here. And then how did I know this 10 to the 6? Well, it's parts per million, and million means 10 to the 6. So again, it's all just about using conversion units and taking a word and turning it into some kind of useful conversion unit. So this one on the left here, this one will allow you to go from grams of carbon dioxide to grams of mixture or vice versa. And this one on the right here will let you go from moles of mercury to moles of solution or vice versa. So you should be pretty comfortable using any of these units. And you'll get more practice in the stoichiometry section there.